welcome everybody. Thank you for coming along to our hackathon. We're here, we're representing Earth Daily Analytics. I'll just give you a little bit of background on the company, who we are, and then we'll dive into the technical stuff. So Earth Daily Analytics is a Canadian company. It's been around for several years now. The headquarters are in Vancouver, a lovely place if you get the chance to go there. And we're offering data from our own satellites, data processing and analytics products. We're going to cover that in a second. I'm joined by colleagues both from Canada and also from France, where we have a partner company, Earth Daily Agro, and we're going to get a quick presentation on that company as well. So who we are, I'm Robin, Rudy, Peter, Nicholas, and Chloe. So we'll be here throughout the day to assist with the hackathon. And a little bit of information about the Earth Daily constellation. So this is going to be our constellation. It's being launched next year throughout. There'll be 10 satellites at the end of the year, providing a daily imaging capability. A little bit of information around the images themselves. So we're going to have 22 channels, and these are complementary to Sentinel-2 in terms of the spectrum. We cover additional parts of the spectrum as well, with some really interesting bands, particularly around the thermal, which we think will be particularly significant for applications like in the agro area. Feel free to take as many pictures as you like. I think this information is all in the public domain anyway. So we're also happy to answer any questions people might have around this capability. I think the graphic in the middle here shows the overlap spectrally with obviously the Landsat and the Sentinel-2 mission. So the thing to take away there is a significant amount of complementary overlap, so you'll be able to create applications that fuse those data sources. EDC is the name of our platform, right? And this is where you'll be able to access all of this data. You probably have heard around Stack. Has everybody here heard of Stack or hearing about it for the first time? Show of hands if you've used Stack or know what it is. Okay, that's nearly everybody. That's fantastic. So I won't go into too much detail, but we're embracing Stack as a protocol for exposing our data, and that's what we're introducing to you guys today. We've got a Stack catalog which we use for our own internal R&D, but we also have a public-facing version of that, and we're hoping that you guys will be able to leverage that to build some exciting applications, and we're here to support you in that process. In terms of the catalog you'll be able to access today, it has Sentinel-1, Sentinel-2, Landsat, Venus, which is another interesting new mission. We can talk about that specifically in a moment. Our own simulated data that will represent what the satellite constellation will be delivering as well. A couple of features which we hope will make our catalog stand out. We're agnostic around the actual platform where the data is hosted, so we support data hosts from AWS, Microsoft and others. And we're also going to be very open-minded about which data sources get added to that catalog, because obviously we want this to become a place where people can come for all of their data needs and build applications which fuse different data sources. So that's what's currently there at the moment. I won't go into that one. So that basically concludes the quick intro to Earth Daily Analytics. I'll hand it over to my colleague Chloe. She'll tell you a bit more about what they do in Earth Daily Agro and introduce you to the catalog, which is the front end to the platform as well.
So hello everyone, welcome to the hackathon. So I'm from Earth Daily Agro. We are a company that has 30 years plus of experience, and we were actually the verticals that will value Earth Daily data for the agricultural market. So the headquarters is based in Minneapolis, and then we have our technical center that is based in France, in Toulouse. So I will show you very quickly the UI that is presenting our Stack catalog. Here we are. Can you see that? Yes, perfect. Okay, so this is Earth Data Store showing the Stack catalog. So basically this is a catalog where you can look for images. So in the email that you have all received, you have some credentials for the API and as well as some credentials for this UI. So you will be able to reach it. And in fact, you can look for all the collections that are available. So you will have some Landsat Sentinel data as well as Venus. So Venus is a scientific mission that has acquired a very specific location, as you can see here on the map, with a frequency that is close to daily, and with a resolution that is around 4 or 5 meters, depending on the mission. And you will have access as well to some SAR data, Sentinel-1 data, and to a collection that is named easily simulated datasets, which is the result of fusion between Sentinel, Landsat, and Venus, as well as MODIS data, to simulate daily frequency, as well as bands that are of highest interest for agriculture. So if you want to do a quick search, then you are looking for example, for Venus. So specify the collection, then you're specifying the dates you are looking for, and then submit, and it will search for all the data that are matching with your criteria. Then you can see different things, all the different properties, look at the image, clicking on those icons.
Chloe, can you also show if you want to search not the whole world, but a particular AOI?
Yeah, absolutely. So if I want, let's say, zoom in here, I can draw, no, sorry, I need to do that again. Oops, sorry. Yeah, so I can draw a polygon of interest, looking for another collection or 2 collections, submit again. And then I will only get the data that are matching my new criteria. There you are.
Pretty big AOI and TOI.
Yeah. I was looking for big stuff.
You're stress testing the system here.
There you are. All right. So here you will go through the difference. If you want some specific coverage in terms of cloud cover, you can also stipulate that. Yeah, here you are.
And if you click on a particular asset, you can see the metadata associated with it.
We can do
which is
that.
quite useful things.
Yeah. So here you have all the item properties that you can get as text or as JSON. If you want to go through, so you will retrieve all the different bands that you usually have in an image. Any questions on that? Yeah.
Yes, so the first search result, we did see the whole world, and now we see the specific area and we see the imagery beneath it, but it's not actually the image which is the result. We have to click on one of those dots to see the actual image, right?
Yeah, in fact, so this is the role of the catalog is really to look for what are the data available within the area of interest and time of interest, but then you will need to go through the images to have more specific details, but this is just to show you how the catalog is working, and you will be able to do exactly the same through the API.
Okay.
So, and then you will get the result of all the items that are matching your criteria.
Okay, so those are basically, this is basically the map intelligence. And can we see one actual picture? Thanks. Okay, can we see one actual result?
Yeah, if I click on this one, for instance, it will get displayed on the mapping module. So here you are.
And if you want to, you can change the visualization properties, like the gamma and the RGB ratio, if you want to as well. If you hover, you know where to put the image on, so you have 3 buttons, so that, yeah, that
This
button
one?
right there. You can also adjust how you wish to actually render the image.
So this is one chip, one map chip? Is it called a chip?
What sensible scene?
Okay, a scene.
It's a
Okay.
tile. Mm.
The image is from Sentinel now. If you turn off like the Sentinel collection, do you receive it from Venus then, or is there?
Yeah, it's
there
because
an image from Venus?
it's because in my research I stipulate Sentinel-2 and Venus. So then the first I have our Sentinels, but then when I scroll down, I will have some Venus one.
Any other questions on the catalog UI? No? Oh yeah, here we go.
What the dot point is representing the center of the image?
What do you mean?
The dot point on the catalog.
There's like a blue dot, I think.
Yeah.
So then those ones?
Yes, is representing the center of the.
I think so.
Okay.
Okay, so for the purpose of this hackathon, we have two flavors of task for you. The first is a bit more machine learning focused, and these are localized within the first two subfolders of the hackathon repository. The second type of task is more focused on data manipulation and visualization. So this will give you a chance to work with our own Earth Data Store API and familiarize yourself with the capabilities of using it. It's a stack API, so all the items that are returned from it are all stack formatted. So you know exactly what kind of metadata you expect to get back. I'm going to run quickly through the stack notebooks section of the repository, and then I'll hand over to Rudy to talk through the UI application that you can use to curate your own data sets. And you can use these later on for the machine learning tasks for inference, change detection. So first things first, how do we get set up? Well, we have a README document at each subfolder level. This kind of gives a brief overview of each of the tasks that you'll be tackling. Kind of just summarizes what I'm about to go through. And then at the very top level of the repository, we have a more general README file, which gives some details about actually getting set up in your environment, etc. So I'd encourage you to read through those before beginning, if you haven't done so already. Second step to getting set up, we have a .env.sample file at each subfolder. And if you just give this a quick copy and paste into the same folder, and then rename this to .env, and then you can basically just repopulate these environment variables with the credentials you've already been provided. Is there anyone that didn't get the credentials by email? No? Okay, good stuff. So that's step 2 of getting set up. Step 3, you just need to pip install the requirements that are specified in the given text document, and you should be good to go. So I'll give a quick run through of the two notebooks that we have in the data visualization section. First of these is basically a time series visualization of an Australian mining site over the period of 1 year. So basically what you'll do is you'll create a series of RGB images for each date in the time period. And at the very end, you'll basically compile all these into a time-lapse video in GIF format that you can then use to exhibit the change in the mining site over time, which for an Australian mining site is obviously pretty significant. So to give a quick run through the notebook, first we just have environment set up, importation of packages. Feel free to import anything else or add anything else that you feel is useful to the task. The notebook really starts around here. We select our satellite mission. By default, we've selected the Venus satellite. Feel free to change that. Feel free to experiment using different bands, etc. as well. Here we just have RGB by default for display purposes. We then specify a region of interest. So this is basically a polygon geometry around our mining site. We then convert this to a bounding box, and we input this into a stack query. So this will query EDS API, which will return a series of different stack formatted items. When we get these items back, they will contain a lot of useful metadata about the data sets itself, stuff like date, time, cloud cover, and other useful meta. We then have some visualization logic for actually just going through these data sets and looking at the temporal distribution of all of the data. So as you can see here, it's very uniformly distributed over the period of the year. And then comes the really important part. It's where we actually stack our data sets and set them up for streaming. So here we've used ODC Stack as a stacking tool. Feel free to use your own if you feel more comfortable with something else. But what this will do is basically combine all those data sets to create an X-array data set that you can then use for analysis and visualization. Finally, we have some normalization, some visualization tools here, and then at the end, we compile all these into a GIF formatted video output that will then display the change in the mining site over time. Are there any questions about this notebook so far? Yep.
So the RAI, region of
Yeah.
How can I know which coordinates are allowed? Because I tried alternative coordinates and no data came back.
This is where the catalog comes in, so you can actually find
Yeah.
the site. So Venus.
Where's the catalog?
So what's important about Venus as well, it's only available in certain regions at certain times. But what Rudy will come to demonstrate, we have a UI platform, and you can actually see on that platform, it's kind of like the catalog that we showed before, but pinpointed on it, you can actually see like what sites are covered by Venus, what time of year. So
Okay.
it could have been the region of interest you put in isn't actually covered by Venus, potentially.
Thanks. And is there any site where the stack API is being documented for all properties? For example, resolution size is 5. If I wanted to have it, something like that?
Yes, that's a really important point. So for example, when we're stacking the images, you will need to repopulate the parameter list with, 10 meters, for example, for Sentinel, etc. But yeah, these are just hard-coded at the moment, so yeah. Any other questions on this notebook?
I think just to mention, you can get the ROI from the catalog UI as well. I think if you draw a polygon on that over an image, you can get the coordinates that you can directly insert into this notebook.
So we have another notebook in here for you as well. There we go. This is kind of concerning building detection. So the premise of this notebook is very similar to the previous one in that we perform a stack query for some Venus data in a given ROI. But this time what we do is we'll just take one of those data sets and we use that in conjunction with this GeoJSON label file that we have on the left. And what we'll do is we'll create a labeled training data set that we can then feed into a classifier or neural network of our choosing and train a model for building detection in the given ROI. The two models that are defined here, we have just a simple logistic scikit-learn logistic regression model. And I think we also have defined like a random forest model that you might want to train, although it takes a little bit longer. But feel free to use whatever, scikit-learn models or otherwise that you like. Any other questions? Okay, I'm going to hand over to Rudy to talk you through the ins and outs of the UI application.
So my part's a little bit less exciting, and I'm not really going to show you any code, but I'm just going to show you a section of the repo which contains something called the Stack app. And the whole idea behind the Stack app is just to give everyone an idea of what you can do with the pieces that we're showing you inside of the repo. So on this tab, what I've done is created this quite simple Dash-based web application where you can do a couple of things. You can select an EDS collection, which is similar to what Chloe showed you in our more formal UI platform. So I can choose Sentinel L2A. I can draw different areas of interest, zoom around. This is Vancouver for context, and maybe I want to draw a little polygon here, just like Chloe did. I can make a date range. I can search for data. In the background, what we're loading here is actually an X-array data set. And so it's sort of ready for analysis and not only for viewing, but of course you might only want to view it. So with a 10% cloud cover, I get 1 day in July and 1 day in August. And what's going to happen now is that from the EDS is going to actually stream the values, not lazy, actually stream the values into this sort of AOI that I have here. You can see it's loading the image here at the top. If we're lucky, it'll actually work for this live demo. And there we go. So what we have here now is this sort of RGB image for our true color baseline and true color comparison. I can kind of zoom in here and just sort of examine, oh, okay, interesting, for these 2 dates, we can see that the tide was at a different level, which caused the sediment in this basin to be manifesting differently in RGB. Now, to make it more interesting, what you might want to do is add like a machine learning classifier, for example. I want to actually segment in this image where the sand is so I can more formally define the change. And just to give an example of that, here we've added an unsupervised segmentation. This is the sort of the simplest thing I could think of. I could press the compute button, and what it's doing is we have that sort of data cube or data set loaded. We run a PCA to compress from 13 to 3 dimensions, and then a k-means clustering to try and
come up with 4 classes here. And again, what will happen is it will compute that and then render it in this little web section of the app. It's loading the values in, and here we get some sort of segmentation of the image. We can see that the layers have expanded to include a comparison segmentation and a baseline segmentation, and we can see, you know, what happens over time, not just in RGB, but also in what our model has thought to be a particular class. Of course, this is very basic. Unsupervised segmentation doesn't even assert anything about what this class is, but this leads maybe nicely into the next thing we want to talk about, which is actually using maybe supervised machine learning models to make assertions about particular classes. So what you can take away from this is, if you want to make something that's visual, maybe you could sort of take the code that's already there, save yourself a little bit of time, and focus more on the machine learning and stuff. You definitely don't have to, but it's a nice little way to visualize your ML applications using the EDS as the foundation. All the code underneath this for the EDS is exactly what sort of Peter already showed, so nothing new on the EDS side. Okay, so you want to go next, Nicholas?
So then we have a third problematic, which is more related to ag markets. So we are proposing you a third notebook, which is about crop identification. So for this problematic, the goal would be to be able to identify crop that has been planted in the field during the season. So the season is not ended, which means that we have a part of the crop cycle, but not everything. And what is at stake here is to be able to have a good knowledge of what is planted across an area of interest, so that we can use that for many different markets. So think about the precision ag market, where the agronomists that are advising growers will be able to have a good understanding of their portfolio of growers and be able to provide the right recommendation at the right time based on the understanding on where I have corn or soybean that are planted and what are the stages of those crops. It's also useful for many other applications, for insurance markets, for banks markets, as well as for commodities market, to be able to have a very good understanding of what is grown in different parts of the world, so related to food security aspects. So here we are proposing an application in an area in the US, in Nebraska, in a small area that is called Mead. So this is a site from the Venus areas, and you will be able, so we are focusing on 3 different years, so 2019, 2020, and 2018. So we are proposing to train over 2018 and 2020 and to evaluate your results against 2019, because 2019 is a particular year in the agricultural markets, because the beginning of the period, or the crop cycle period, was really rainy, so we have a delay in the plantation. So if your model have very good results on that year, it means that it's a very good one. And so I will, Nicola, give us more technical details, but we are proposing 2 flavors in terms of models, one machine learning and one deep learning models.
So everybody, so for this case, we use 3 years of the simulation. It is the fusion between Sentinel-2, Landsat, Venus, and MODIS data. MODIS is just for the thermal sensor. So we pre-generate for you the years in order to do not download the data from the internet. So it will be easier to iterate between the models. So it's the same thing as earlier when you run Python script. So you have the data for each year, 2019, 2018, and 2020. Fields can change among years. So for each year, you have the field shapes and the data of what crop is in this shape. So with that, we can explore the data So I did not run this cell, so you can do it later in order to explore the data, to know where are the crops, what kind of crops do you have. So it's mainly soy and corn in this place. And after, there is a code that generates the data for you, but you have that already downloaded. But if you want to try some new things, you can do it, but it can take some time. It depends on how much data you want. So this code has already been run for you. And it is the same thing as earlier. We ask for the Earth data store catalog, and we are asking for this band. This is only the visible and near-infrared band for the simulation, but you have other bands like the SWIR band or the thermal band you can maybe want to add in this hackathon. And after the data is generated, I just randomly choose some field. So here there are some corn from 2020. This is just one field. This is the mean value of this field in the NDVI. I think everybody knows what is NDVI. No? This is the difference between the near-infrared and the red, divided by the near-infrared and the red. So it gives you, when the NDVI is higher, it means that the vegetation has grown.
Deviation.
Yeah. It's a normalized difference vegetation index. So it's very useful in order to show what is going. So here you can see that the corn is growing, and then the vegetation is lower. So it means that we certainly cut the corn. So we have this kind of plot for corn and soybean. You see a different trend. So when we compare them, soybean has a NDVI that is later higher than the corn. So you can see there's a difference in trends.
What's important in the crop identification is that the earliest the model is able to detect it, the better it is, because of course everyone wants to know very early what is planted during the season, because you then can make more decision about it than if you understand what is your landscape very late when this is close to the harvest period. So ideally we would target something like being able to identify quite accurately what is planted in June. So just to set up expectations for your results.
Yes, you have all the season, but for the training dataset, we want to stop here. So it's very early in the season. So for the corn, it's almost at the highest point, but for soy, it's at the beginning for this year. Then this is the data you have for the training dataset for 2020, but it is the same date for 2018 and for 2019. We have the same sampling range. And then you can ask for the training and the training data with the label data, which is the most important thing, the labels. And so if we plot all the data we have, so it's about 8,000 fields. So we have this soy NDVI. So we can see that some fields are not labeled well, we think, because it's from another open source data. So maybe you have to do some cleaning, I don't know. It's up to you. And this is for the corn. So we see the same delay, but we stop at the 1st July. This is why we don't have the same trend before. And this is for Mido, which is a totally different curve. And so with the X data, which are the spectral bands, and the Y data, which are the labels, we can do some machine learning now. So you have the template of the basics. So after you can do everything you want to enhance your results. So you can maybe just select random forest or XGBoost. And then you can do something like my model, which is a random forest dot fit my data with X and Y, which is a label. And then you predict, and you have something like that. So this is not a very high accuracy, but this is just for the demo. I think you can do better than me, and I hope. And so you can see that this is very imbalanced. We have a lot of data for corn and soybean, and we want to predict well corn and soybean. The other data is not what we want to enhance because it's sometimes not the season, not the right season to predict them. So here I just learned with 2018 and predict on 2019, but I can do the same with 2020. So I train with 2020 and I predict with 2019. So I have a better result. And so maybe you want to train with 2018 and 2020 and see what happens to predict 2019. And this is what happens. So this is the basic ideas. So you can add some cross-validation, I don't know, a lot of methods to enhance the results. So this is for the machine learning part. And if you want to try some deep learning, we select the LX model, which is a specific model for the crop detection in season. So it's a very promising model. It's open source, and it's work using PyTorch. And so I just code a function in order to convert the data we used previously for the random forest to be compatible with the PyTorch. So it's the same templates. And so we can do something like my model, which is LX.train, train and test. And then we have this result for deep learning. The difference between machine learning and deep learning for this aspect is that when you use LX, you need to have... Just wait. Thank you. So the deep learning model is a very specific model which needs the same input dimension for each date. So you cannot have SAR data at some date and not SAR data at other dates. So if you have 10 bands per date, you need to have 10 bands at every date. So you cannot add just one feature. You need to add, if you have 10 dates, you need to add 10 features at once. So this is a bit particular for this learning model. So you can add, like example, the weather data. If you have some weather data for every date we have, you can add the SAR data if you sampled the same date as the visible data, but you cannot add just one SAR data, one date. But you can do that with random forest. So if you want to train with 2 years, you can. It's the same, and you have this kind of confusion matrix. So if you want to add weather data, you can add weather data. I don't give you the API, but we have some API available maybe on the internet, and you can add the global feature for the data. I can help you if you need help. Or, for example, you can add Sentinel-1, which is a SAR data, and then train with the Sentinel-1. And here it's really easy to add Sentinel-1. So we just use the EarthDaily Python package, and it's eds.datacube. You specify that, and you have your SAR data ready to train. So that's all for this project. Do you have any questions? Yes.
Yes. So can you help me out with the data itself for this data science part on a high level? Are we talking about analyzing the images or images and metadata from the images, or because I saw the pandas data frame?
Yeah.
So how does it work?
So we have the image, and for each field, I just compute the mean value for each band at each date. And so you have a NumPy array, or Panda if you like. And so this is this kind of data that you are going to use to train the data. So
what data is it?
It's the spectral values. So for each field, you have, for each date, like 10 spectral values because we have 10 bands.
Okay.
And this thing is going into the model.
Like color, contrast, stuff like that?
This is the raw values of the spectral bands. This is the blue band, red, the infrared band.
All right.
Yes.
Okay, thanks.
Any more questions? No? Okay, great. I'll just finish up, just a bit of, covering what's coming. So everyone should have received their credentials already. If anybody hasn't, just give us a shout. We've got all that. We can get you set up. Obviously, in terms of time, we've got lunch between 12:30 and 1:30. We're planning on being here till 6 today, and what we'd love is to see, what you guys can do in that time. There's, in terms of what we're looking for, we're really looking for innovation and impact, I think. So you can come up with a new UI, a new way of integrating machine learning into the UI, or even just work on the modeling itself. You've got all of that scope there. We do have prizes available. These are going to be, I think, Amazon gift cards. And what we're looking is, we've got a spreadsheet. And so if you want to make an entry with what you've done, get the code on GitHub, put the link into the spreadsheet, and we're going to look at that this week. And then on Thursday, we'll have a decision, which are the prize winners, and we'll announce the prizes, but we're also going to follow this up. So there'll be some promotion after the end of the hackathon. We are running another hackathon in the new year, so we're kind of hoping this one is a chance to learn about what kind of problems people are really excited about and what kind of things they can bring. So, even if you don't win a prize this time, that knowledge can be used for the next hackathon as well. So has everybody got a few ideas, things they want to work on? And the other thing we can do is if you want to pair with somebody else in the room, we're happy to facilitate that as well. We'll also be available to assist you in your efforts today as well. So yeah, let's dive in. Oh, we've got a question over here, yeah.
Can you use pre-trained models?
Yeah, you can do whatever you want, yeah. So, and obviously, you've got all of the information available in the stack catalog there. We had a question about what other features you could potentially bring in. It could be from the catalog, external sources, go wild, just whatever you think will improve the results. So, yeah, fantastic. Okay.
I mentioned, we know this room is maybe not the most ergonomic for working, so we also there's some standing tables outside where you can at least stand up and work on those tables. If you want to go to another part in the conference that you find that has a nice working table, it's also good. We'll probably be sticking around here just to be easy to find, but don't feel that you need to sit in these chairs all the time if you want to.
Yeah, cool. I think we've got another half an hour or something before lunch. So I think what would be great, if you're not sure where to start, just try and run maybe the stack notebooks to begin with. Use the catalog, just make sure you've got all the credentials. That will be a really nice introduction to how the catalog and the API tie together, and then just take it from there. So yeah, I really gave a good example of where you might get to. I think that's maybe a day's work that went into that. So, give or take, we might see something similar or different today as well. So, okay, all right, well, I'll hand it over to you guys, and best of luck hacking. Thank you. Welcome back, everybody. Thank you for making it through to almost the end of the day. Approaching the highlight, I think, which would be to see what people have been working on. So can I just have a show of hands who wants to do a quick presentation? Bearing in mind there's $600 of prizes as well. So we've got one. Anybody else? Two, three. Anybody else? Everyone's going to win $200. That's amazing. Fantastic. So any volunteers to go first? Yeah, you're happy to go first? So, okay, come on over.
Okay, so we tackled the third challenge, the crop type classification challenge. Giant, Max and me, Stefan. And we tried to integrate an additional dataset called soil grids, which has a 250-meter resolution. We trained a model using LSTM, and then we tried to fine-tune an additional pre-trained model and use an ensemble approach. And then the idea was to create an interactive app where you can select a polygon on the map and then use this new data time series to infer the crop type using the model that we trained. So we created already a prototype of the map. We accessed the data for the soil grids, and we created a data pipeline for the model training. We have the pieces in place, and now the next steps would be to integrate the pieces, put the building blocks together, and then have an end-to-end solution.
There we have it. I haven't done anything innovative here. I just implemented some filtering of the training data. The demonstrated data here is not the training data, though it's the 2019 data, where I just demonstrated the filtering approach. And the filtering approach is simply to sort the values, and I removed the lowest 1% and the highest 10%. And I just did that by filtering on the third date, because there I saw that it was a big variation. So it was a really, really simple approach, and it could, of course, be improved by making some more dynamic model that can look on the entire time series and everything. And the results are not that good either. For the model that looked at the 2018 data, I think it's slightly improved in the corn detection section there, but the rest is worse. And for the other data sets, it's got a lot worse. So you can probably tinker on with that filtering a lot more and make it more dynamic. And that's about it.
All right. So I did not achieve much, but I learned a lot. And I started by modeling a utils, blah, 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 here. So where's the lat long? No. Store data set images. Yes. So I started with this one. You pass in a lat long, and you get the coordinates and the GeoJSON. And using that, I found out that you cannot get all the images. Not every satellite has the images for every part of the world. But I was interested in two things: segmentations. I can show you that because they're mostly black. So I have to do a lot of work in converting that. But I created my own NDVI, right? So normalization of vegetation and the differentiator. And the results, I mean, I'm generating the GIF. I don't think it worked. Let me try. Because I was just, yeah, it worked. Yes. Thanks. Hey, you can applaud me. Yeah. It was quite difficult. So what I'm doing here, I'm trying to, what I wanted to achieve was two things: segmentation of area segmentation, like where is land, where is water, where is something planted, vegetation. But then I just focused on water, and so I tried to make it blue. I could not, but I worked with the infrared, infrared band, with the infrared band to sort that out. And I have something really wrong here with the colors, but yeah, that's how I could do it. So that's what I achieved. And also, with my colleague, we were doing the interface for the UI so that we passed this X-array data set We get the X-array dataset from the UI selected by the inputs from the user. We process it this way and give it back to the UI. So just, yeah, that's it. Thank you.
Well, thank you for the presentations, everyone. It's really nice to see what you've done with the material we've prepared today. Need to make sure I get the names of everybody because everyone's going to win a prize. We'll make the announcements on Thursday at the closing ceremony, and we're going to share this video with our colleagues back in Canada so they can see what everybody did as well. So just to make sure we got your names and emails, we have a spreadsheet, a CSV. If you can access that and just put your for one from your team, and you guys can put your own names there as well. We'll be in touch with the details about the prizes. Okay, well that concludes everything for today. Thanks again for showing up. We will be running a follow-on hackathon in a few months' time, and we'll be sharing information on that as well, but hopefully we'll see some of these faces back then. So once again, thank you.
Thanks everyone. Thank you.